So in this video, I want to talk about Taylor series. This is a continuation of a topic we already talked about in class, but I want to have everything all in one nice, succinct place. And so what I want to do is I want to kind of rederive the formula that we talked about in class, or at least mention it again. And that's if we have a power series for an arbitrary function f. Okay, so when we talked about power series before, we kind of leveraged everything that we could off of the geometric series. And so if you had any function that kind of looked like that, then you could use the geometric series to get a Taylor series or a power series representation. Taylor series are how you do that for arbitrary functions. And so here what we're going to do is we're going to notice that if we have a power series representation of f, and if we compute the nth derivative of f at a, you end up getting n factorial times c sub n. Okay, and so that's what you end up getting as a formula for the nth derivative of f at a. And in particular, these terms, c sub n, are the nth derivative of f at a divided by n factorial. And therefore, a Taylor series representation of a function is a power series of the form the nth derivative of f at a over n factorial. So this is a way that you can get a power series representation for any function, regardless of whether it has this geometric series structure or not. Okay? And so we did some examples in class. We did some examples of e to the t, sine of t, cosine of t, and so on. Okay, and so what I want to do is I want to actually show you a few things before we do this. I want to show you something in general. And that is, if you have a power series representation, think about what the first few terms are. You have the 0th derivative of f at a, that's the original function, divided by 0 factorial, times x minus a to the 0. And then you have the first derivative of f at a, divided by 1 factorial, times x minus a to the first, plus the second derivative of f at a, divided by 2 factorial, times x minus a squared, and so on. You'd have the third derivative of f at a divided by 6 times x minus a cubed, and so on. All right. So what I want to do is I really want to emphasize here, notice the first two terms in the series. Okay, so notice the f of a plus f prime of a times x minus a. That is exactly what we called in section 2.9 in Calc 1. That's what we called the linearization of f at a. And so the linearization is f of a plus, it's exactly the same quantity, f prime of a times x minus a. And this is really just the tangent line. Linearization is just a fancy way to say the tangent line. And the point here was that if you have a function and then you draw its tangent line, well, you can estimate the value of the function by the value at the tangent line. Okay, so let's say you understand what the function is at some point. As long as you move not too far away, then these are pretty good estimates. Okay, so maybe the function dips like this, and the tangent line is going to go like that. And so maybe away from this point here, there's quite a difference between these two. But locally, near where you have a tangent line, the function and the tangent line are approximately equal to each other. That was the main idea in section 2.9. Now, we had some errors in there. And so I want you to notice that if you want a better estimate, instead of using the linearization, you can use the first 3 terms or the first 10 terms. Okay? And so we'll talk about how many terms in a Taylor series you need to add so that they're accurate to however many decimal places you want. Okay, so if we want to estimate the value of a function at a point, we can use Taylor series, and then there's kind of a formula that tells us how many terms in that Taylor series do we need to add up to be accurate to however many decimal places. Okay, and so that's really one of the big places where Taylor series are useful. Okay, so this is a generalization of section 2.9. Taylor series are in a lot of ways kind of a big picture encapsulation of like everything that we've done so far. It really kind of puts everything in perspective here. So that's the first thing I wanted to show, is that Taylor series are kind of Taylor series are actually or things like Taylor series are ways that your calculator can actually compute values of a function at a certain point. Okay, so Taylor series get used all over the place with that kind of stuff computationally. The next thing I want to talk about in this Taylor series squared at 0. And these are, remember that Taylor series are the name that we give to these types of series. If A is equal to 0, then you get what's called a Maclaurin series. There's just a special name for it. So f of x is then the nth derivative. It's the sum as n goes from 0 to infinity. The nth derivative of f at 0 divided by n factorial times x minus 0 to the n. Okay, so that's called the Maclaurin series. And I want to find the Maclaurin series for a few different functions. So let's find the Maclaurin series for, let's start with, and I'm not going to go through the work here. I will do a video, probably the next video, where I do a few of these by hand, but for now I'm just kind of recapping what we talked about previously. E to the t is going to be t to the n over n factorial. So the nth derivative of e to the t is 0, so it's just 1. So 1 over n factorial. Using t, because this helps us kind of, if we wanted to find e to the x squared, if we wanted to find, say, e to the x squared, this would just be the sum as n goes from 0 to infinity of x squared to the n over n factorial. Right? You could just replace whatever you want. Replace the t with whatever you want, and then this can, this is how we could find a Maclaurin series for all of that. So this Maclaurin series e to the t is super important. This is, let's see, as n goes from 0 to infinity, we end up with 1 plus t plus 1/2 t squared plus 1/6 t cubed, okay, and so on. This is valid, by the way, for all real numbers. So this is a power series with radius of convergence infinity. So that's the first one to know. The next one to know is sine and cosine. So I guess those are two. So the next two to know are sine and cosine. And they're very similar. They have kind of a similar pattern. For sine, you get the negative powers. So you get negative 1 to the n, t to the 2n plus 1 over 2n plus 1 factorial. I don't mean negative powers. I don't know if I said that. You get the odd powers. So you get t to the first, t cubed, t to the fifth, and so on. So sine of t is equal to t minus 1/3 t cubed plus, minus 1/6 t cubed is 1 over 3 factorial plus 1 over 5 factorial t to the fifth, and so on. Cosine is going to be the same thing, except all the 2n plus 1s are 2n's. So you get negative 1 to the n, t to the 2n over 2n factorial. So that turns out to be 1 minus 1/2 t squared plus 1/4 t to the 4th, and so on. Okay, minus 1 over, and again I did it again, I forgot the factorial. For the 2, it's okay, because 2 factorial is 2, but for 4 it makes a difference. This is 1 over 24 t to the 4th, plus 1 over 6 factorial, which is 720 t to the 6th, and so on. Okay, so that's sine and cosine. And one of the things that we get for sine and cosine, oh, and I forgot to say, I'm sorry, that for these, r is infinity as well. Okay, so that's very nice. So the radius of convergence is infinite there as well. One of the things that we get from here, almost for free, one of the things that we get there is formulas for not just sine, and so it turns out what we have to do is get rid of the power of negative 1. And if we do that, then we get our formulas, and that's cosh. It's the same as sine and cosine, just without the powers of negative 1. That basically just means that it doesn't alternate. Okay, so every term there is positive. Other power series that we've talked about include the geometric series formula, so 1 over 1 minus t. Okay, so it's kind of our old friend at this point, sum from 0 to infinity. This is 1 plus t squared and here, r is equal to infinity. So this is only valid, r is equal to 1. So this is only valid where we actually valid t is less than 1. So t is between negative 1 and 1. We talked about the natural log of 1 plus t. Okay, and so what you do here is you differentiate and integrate. Remember, this is the derivative of, the integral of the derivative, which is the derivative is 1 over 1 plus t. This is now like a geometric series, and when you do everything out, there's some steps. This was in my video in the last section 11.9. It turns out what you're going to get is n plus 1 times t to the n plus 1, and then this alternates, negative 1 to the n. So that's the natural log of 1 plus t. So we talked about that. We also did one for arctangent. If you want to write that one down, feel free. I'm just going to stop here. Okay? And so those are the Taylor series that we know for now. And I want to just point out a few things. These are Maclaurin series, by the way. But I just want to point out, if I wanted to find, say, the tangent line or the linearization of a function, it's now trivial if you know the Taylor series, right? The tangent line of e to the t at 0 is 1 plus t. The tangent line for sine at 0 is just t, because that's you could think of this as 0 plus t. The tangent line for cosine at 0 is just 1, because it's 1 plus 0t, right? And so all of these are pretty easy. The tangent line for 1 over 1 minus t is 1 plus t. Okay, so the tangent line now comes basically for free if you have the Taylor series. All right, in the next video, we'll do some examples of doing this by hand for some other